my favorite dimensions is the fifth dimension. It's very cool. And one of the reasons that I like it is it has, mathematically speaking here, the largest balls. Well, let me tell you what I mean. In school, we learn formulas like that the area of a circle is pi r squared, and that the volume of a three-dimensional ball is 4/3 pi r cubed, where r here is the radius. But did you know that there's actually a whole family of different formulas as you go up in dimension? They all have the format that there's some coefficient times the radius to whatever the dimension is. If you're in dimension 3, it's 4/3 pi r cubed because 3 is the dimension. But if I plug r equal to 1 into this table and sort of approximate what those coefficients are, you'll see that the largest value of those coefficients happens in dimension 5. Okay, so in this video I'm going to tell you what even are these higher dimensional spheres, where do these formulas come from, and what happens if you play around with the notion of what a higher dimensional ball even is. Okay, so back to the circle. This is the circle of radius r, centered at the origin, and I'm going to define what I'll call the two-dimensional ball B2, and it's going to be all pairs xy, such that their distance from the origin is less than r. And I capture that with this formula that the square root of x squared plus y squared is less than or equal to r. This is just the Pythagorean formula, and that is going to be my definition. All points, distance less than r from the origin. Similarly, I can go up into 3 dimensions and I get the three-dimensional ball B3, and it's all triples of numbers, x, y, and z, such that an analogous formula holds, the square root of x squared plus y squared plus z squared. That's how you measure distance in 3 dimensions. You can actually go down all the way to 1 dimension and have what I'll call the one-dimensional ball here. It doesn't look very round, it's just an interval, but it follows the pattern. In 1 dimension, there's one coordinate x, and it has the condition that the square root of the sum of the components squared, so the square root of x squared, is less than r. And that just gives me an interval from negative r to r. I could replace the square root of x squared with the absolute value. It's the same thing. So I really have formulas for the one-dimensional ball, the two-dimensional ball, and the three-dimensional ball. It's not hard to come up with formulas for the four-dimensional ball. It's just the same thing. 4 coordinates now, x, y, z, and w, and a similar kind of formula, the square root of x squared plus y squared plus z squared plus w squared is less than or equal to r. And indeed, I can go all the way down to the n-dimensional ball. It would just have n components. So without visualizing, just thought of in terms of this definition, higher dimensional balls aren't all that bizarre. They're just lists of numbers that obey a particular square root condition. Now, I want to show you a trick about how you can visualize the 4-dimensional sphere, but let's build this trick up by thinking in 3 dimensions. If I start with a sphere, I can imagine slicing along that sphere at a particular location. If I look on that slice, it appears to be a circle. And as I move my slice along, you can see that the size of the two-dimensional ball that appears gets larger and larger until it hits the equator, and then smaller and smaller after that. So we can work by analogy up a dimension. I can't visualize authentically what the 4-dimensional ball is, but I can imagine slices of it. If I have a 4-dimensional ball, its slice is now a 3-dimensional slice. I always want to go down 1 dimension, so it looks like a portion of a cube. And then as I take this 3-dimensional slice and move it around through the 4-dimensional ball, you see that its slices appear as spheres. So this method of slices gives us one way to try and visualize at least a little bit of what a 4-dimensional ball might be, even if I can't visualize the entire thing all at once. So now I want to understand why the 5th dimension? Like, what made the 5th dimension special that it had the largest of all of these volumes? And to do that, I'm actually going to investigate not spheres, but cubes. So these are the cubes, I'll call them Cn now, and they consist of every component, x, y, z, however many they are, being between -1 and 1. So in 1 dimension, I'm going to have, well, it's just an interval going from -1 to 1, and its length is 2. In this video, I'm going to be using volume a bit loosely, so I might talk about length, but I'm also just call it one-dimensional volume. Then in 2 dimensions, well, now I have a cube where both components go between -1 and 1. That breaks up into 4 unit squares, squares of area 1. So its area is 4. For a cube where every component goes between -1 and 1, that breaks up into 8 different unit cubes. And so the volume of this 3-dimensional cube, well, it's 8. And if you carry on with the pattern, you just get the volume, or sometimes we'll say hypervolume if we want to indicate it's a higher number of dimensions. We'll call it hypervolume. But either way, the volume of an n cube is 2 to the power of n. So the takeaway here is that as I increase the number of dimensions, the volumes are getting larger and larger and larger. Now, I know they don't have the same units, but the magnitude of these volumes are getting larger and larger and larger. And so this gives some intuition, at least, as to why, say, the volume of a sphere is larger than the area of a circle. We've increased the number of dimensions. As we see here, increased number of dimensions makes things bigger. But there's something working against this property. So let me put up here now the two-dimensional square and the two-dimensional circle. And you could ask the question, well, what percentage of the square does the circle contain? And well, if you do the math, it's pi r squared, right? So pi 1 squared divided by the area of the square, which is 2 times 2, or 4. It's about 79%. The circle takes up 79% of the square. Okay, well, what about a sphere inside of a cube? I'm actually first going to do the cylinder inside of a cube. And the reason I like the cylinder is because the cylinder is the same formula. At any slice, it looks exactly like the area. So this is yet again 79% of the total cube. But then if I take the cylinder and I squish the top and bottom ends to it to get a sphere, I've got something smaller, right? If I actually want to do the math here, it's 4/3 pi r cubed, so 4/3 pi when the radius is 1, divided by 2 cubed, that's 8. The sphere only contains 52% of the volume of the cube. And by the same argument we just saw, where we could imagine in higher dimensions taking this circle, extending into a sort of a higher dimensional cylinder, and then making it smaller to become a higher dimensional sphere, it makes sense that as you increase the number of dimensions, it's a smaller and smaller percentage of the cube. So when you put both of these two things together, the cubes are getting bigger and bigger and bigger. They're doubling in volume every single time. But the percentage of the cubes gets smaller as the dimensions goes higher. And so when we look at this formula, these formulas are really balancing these two different things that are occurring. And it turns out that in dimension 5, that's where the tipping point happens. That the shrinking percentage of the boundary box that represents what spheres are doing dominates the fact that increasing dimensions are going to double the total size of that boundary box. 5th dimension is the crossing point between these two features. Now, we'll gain a bit more intuition when we try to come up with some actual formulas for how to come up with these. I'm going to first prove to you the 4/3 pi r cubed one, the 3-dimensional one that perhaps you already know. Then we'll use that construction to basically generalize and get everything else pretty quickly. So I'm going to construct a 3-dimensional ball in a bit of a weird way. I'm going to add up a whole bunch of cylinders. They're all concentric cylinders. And if I add them up with just the right heights, you'll notice that you get something here that looks a little bit like a sphere. And if I subdivide a little bit better, if I use more cylinders more accurately, you get a better and better sphere. And so the idea here is to use something called cylindrical coordinates, where if I add up all of these cylinders and I do this sort of in a limit as the cylinders get small, then I'll get to the volume of a sphere. And so what I'm going to do is come up with this messy integral formula. So if you've seen some calculus before, this is a really lovely derivation. I hope you enjoy it. If you've never seen any calculus before, well, feel free to hang around here or skip to the next timestamp. So the way I'm going to do this is I'm going to build it up piece by piece. I'm going to start with a disk in the xy plane, and I'm going to put a little patch on that disk. And this little patch consists of a small change that we call dr in the radius, the distance away from the origin, and a small change in theta, what happens if I rotate around the origin. But then I'm going to go, instead of just a patch, I'm going to go from the xy plane all the way up to the top of the sphere, and I'm going to claim this weird square root. Well, what I really have here is a triangle that goes from the origin. The hypotenuse of my triangle is 1. By the way, I'm going to do a unit sphere here. If you want to extend to an arbitrary sphere, that's totally fine. The horizontal component is going to be r. I'm imagining my little patch lives at a distance r. And so then, by Pythagoras, the height of it, that's what I'm interested in, is the square root of 1 minus r squared. Then I'll try rotating that little strip all the way around. So this is a rotation of theta by 2 pi. So that's what my integral sign from 0 to 2 pi does. And then finally, it's not just from the top, it's from the top and the bottom, so I have to multiply everything by 2. This is my formula. And now that I have this formula, I can pretty quickly compute it out. I think what I have to do here is a u substitution because I got all that weird square root of stuff. I'm going to clean that up. So u is 1 minus r squared. And if you plug that in, I'll let you check the work, I'll go through quickly, it just becomes, well, an integrand of 2/3, integrate out by the 2 pi, and you're going to get 4 pi over 3. So I apologize for speeding through, but the point I want you to take away from this is that effectively it's a double integral in cylindrical coordinates to compute out the volume of this 3-dimensional ball. But how can we make the leap from 3 dimensions into a higher number of dimensions? I want to tell you about a principle. Imagine that I just have a unit circle here. As we know, its area is pi times 1 squared, or pi. If I double the size of this particular circle, you're going to get this circle, which has now got area pi times 2 squared. The radius is being doubled. So going from 1 squared to 2 squared is a multiplication of 4. Now, in general, the way this works is I'll define what I'll call VNR. So this is the volume in n dimensions of a ball of radius r. And the lovely thing is that there's a formula that relates this back just to the volume of a unit ball of Vn of 1, where the radius is equal to 1. And it just says there was a stretching factor of r to the power of n. So in 2 dimensions, when our radius went from 1 to 2, the stretching factor was 2 squared. It became 4 times larger. And this actually isn't about spheres. This is very general. Like here, the blue object was just a stretching by 2 in both dimensions. And so the blue object has 4 times the area of the purple object. Nothing to do with circles. This is a general property of how we talk about area and volume. So we're going to use that translation property to adjust the proof that we just did. So let's go back to it. Remember where we were. We had this formula for the volume of a unit sphere, and it had been based on this idea of taking this particular strip. But let's take another moment to look at the strip. This strip has total height 2 times the square root of 1 minus r squared. And funny thing about that 2, remember how I told you the one-dimensional ball was just like an interval from -1 to 1? The length of a one-dimensional ball was just 2. So if I look at this, that 2 can be thought of a bit differently. This can be thought of as the one-dimensional volume of a one-dimensional ball, again, just an interval, just a length, of square root of 1 minus r squared. And that's particularly nice because now I can use this as a metaphor for jumping up to a higher number of dimensions. Like, let's imagine you have a 100-dimensional ball, whatever you like. You could always imagine taking 2 of those dimensions, putting an r and a theta in those 2 dimensions, and drawing this kind of picture. The vertical strip now is not necessarily one-dimensional. Like if it was a 100-dimensional ball, your vertical strip is going to be 98-dimensional. But whatever it is, it's 2 dimensions removed. So in other words, I could rewrite it as this. This is just a picture to illustrate the analogy. But if you're in n dimensions, then you can imagine taking 2 of them to the r and the theta, and then all the other dimensions, the n minus 2 dimensions, go into the Vn minus 2, and it has this stretching factor of square root of 1 minus r squared. We're going to be getting this recurrence relation, this relationship between Vn of 1 and Vn minus 2 of all of this stuff. Okay, so let's see if we can study this. Well, the first thing that we can do is we can use that proportionality relationship we just seen. Instead of the n minus 2-dimensional volume of square root of 1 minus r squared, we'll make it the n-dimensional volume of 1, and then we have a stretching factor. What's our stretching factor? Well, you take whatever the radius is, square root of 1 minus r squared, and you raise it to the power of the dimension, to the power of n minus 2. Vn minus 2 of 1, that's just a constant. It can come out the front if we so wish. And now the proof proceeds basically exactly as we did before. First of all, there's a u sub to clean up the mess, so I'll make 1 minus r squared. Let's just set that as our u. If you figure out what du is and plug it all in, well, you can plug that in and you get this particular integrand, u to the n minus 2 over 2, and then divide it out by -2. And again, if you evaluate that at the endpoints, well, you're just going to get 1 over n. There's a final integral to do, the integral from 0 to 2 pi. That just adds a 2 pi. So what do we have? We have this final formula. Vn of 1 gets related to Vn minus 2 of 1 times 2 pi over n. This is a recurrence formula. And this is so great because once I have this formula, I can figure out everything. So like on our list, as long as I had dimensions 1 and 2 figured out, I can now always jump back. Like I can figure out dimensions 3, 5, and 7 based on dimension 1. And I can figure out dimensions 4, 6, and 8 from dimension 2. So in just the same way, earlier in the video, we derived the volume of the 3-dimensional sphere from the 1-dimensional sphere, we can now get any of the ones on this table. So that's our derivation of the volume of an n-dimensional ball. By the way, because you have this multiplication of like 1/5, 1/7, 1/9, and so forth, it feels a little bit like a factorial. And in fact, there actually is a formula for it. If you want to put it all together, instead of a recurrence relation, you can call it this formula, which is pi to the n divided by 2 divided by the gamma function of n over 2 plus 1. And we could go into the gamma function before, I've done other videos on it, but all I want you to really take away is the gamma function behaves a lot like a factorial does. So in fact, if you take in a positive integer, it just becomes a factorial. The gamma function of n is just n minus 1 factorial. But it also allows other values like n plus a half, that's something that shows up here, becomes something very similar to a factorial. It's like n minus a half times n minus 3 halves, n minus 5 halves, all the way down, and then sticks a square root of pi at the end. It's a funky object, but the point is there's this nice formula that I can go and put into the computer and get Python to evaluate the values of if I wish. Now, everything that we have done so far relied on a certain notion of what higher dimensional spheres were. Like, remember, for the circle, our defining characteristic was it was points where the square root of the sum of the squares was less than the radius. And this came to us from Pythagoras, so it's the sort of standard and normal definition of distance. But I can imagine this being a special case of a more general formula. Instead of square root of x squared plus y squared, how about x to the p plus y to the p to the power of 1 over p? P is 2, it's the same thing, but I could imagine p being a bunch of different things. These are sometimes called p norms, and p equal to 2 being our special case. In 3 dimensions, it's the exact same thing, right? Instead of the square root of the sum of the components squared, you can imagine it's the components to the power of p all to the power of 1 over p, and our special case of p equal to 2. So what do these look like? I can play around with my circle, so if I reduce the value of p from 2 down to 1, this is the shape of all points whose distance is less than 1 from the origin in this new notion of distance. This notion of distance is useful, by the way. It's sometimes called the taxicab metric, and it represents a situation where a taxi can only move horizontally or vertically. It cannot move diagonally. If I increase the value of p, things start becoming more and more looking like a square. This is also a useful notion of distance. Like in the game of chess, your king can move to the left and the right, up and down, but also in one move can move diagonally. And so you can imagine this square is all points of distance 1 in this funky notion of distance. In 3 dimensions, our unit ball, well, if I shrink the p down to 1, is going to become this lovely octahedron. This is the 3-dimensional version of the taxicab metric. As I grow it out larger and larger, it's going to approach asymptotically a cube. So we have these different notions of what an n-dimensional ball could look like depending on that value of p. There's actually a formula for this. Again, it's defined in terms of the gamma function, which is very useful. All I really want you to take from this is that because we have this formula, and it can be derived basically the way we did it, it's not that much of a leap from what we did to get into here, is that now I can just plug this into the computer and I can program the biggest dimension for any particular value of, and indeed I did precisely that. So here we're back in the original p equal to 2 case, the normal notion of distance, and we see that dimension 5 has the largest volume. If I take my p and shrink it down to 1, well, it turns out that dimensions 1 and 2 share the equal largest volume. Basically, for p equal to 1, we're just cutting out too much of our volume, so it doesn't really grow as the dimension increases. In contrast, if I increase the value of p past the value of 2 to larger ones, we'll notice that this shifts the maximum volume to the right. And indeed, as p gets larger and larger and larger, the maximum dimension gets larger and larger as well. Now, to learn more cool math, I strongly recommend the sponsor of today's video, which is Brilliant.org. Brilliant is an online learning platform that helps you achieve your learning goals in math, science, and computer science. They use a really effective design that breaks up large and complicated ideas like how an LLM works and puts that into bite-sized pieces. All their modules are really interactive, so you actually get to play around with the animations, write your own code, make predictions, and you're constantly given opportunities to test your own understanding to make sure that you really mastered each and every piece. With regular practice over time, I believe that anybody can learn math and use that math in their careers. And Brilliant does a great job of supporting that kind of learning journey. To try everything that Brilliant has for free, go to brilliant.org/trevorbaz or click the link down in the description. And clicking that link will also give you 20% off an annual premium subscription so that you can get unlimited daily access to everything that Brilliant has to offer. With that said and done, if you have any questions about this video, leave them down in the comments and we'll do some more math in the next video.